Hi, I'm Guang, 50 years old. In this lesson of the techniques and applications of definite integration, we'll be taking a look at this example here. And this example is about your double integration. Within, you have the integrand of square root 1 minus x squared over a squared minus y squared over b squared dx dy. So for this kind of an integration, when you see both x squared and y squared, you might be thinking of polar coordinates, right? But you have to be aware, this boundary is now x is equal to ar cosine theta and y is equal to br sine theta. Not really your normal polar coordinates that you'll see, since normally you would see x is equal to r cosine theta, y is equal to r sine theta. But this time you have a and b. Well, a and b are not necessarily equal to each other. So r is from 0 to 1, while theta is from 0 to 2 pi. So can you imagine what this graph would look like? Since a and b, they do not have to be equal to each other. So it's not necessarily a circle, it could be a circle, but what would you call that kind of a shape? Well, of course, you would just call it an ellipse. Alright, so x, y, and here's your origin. So how would your ellipse look like? Since x is equal to ar cosine theta, that means along your x-axis would be your a, while along y-axis will be the b. Right, so it would probably look something like this. So for this ellipse over here, you can have a greater than b or b greater than a. But for the one that is greater, that will be your major axis, while for the one that's smaller, it will be your, of course, the minor one. Alright? So now that we know this is an ellipse, and the ellipse from 0 to 1, that means it will be for everything within here. Right? So how are we going to integrate this now? Now, since this is not your conventional x is equal to r cosine theta, y is equal to r sine theta, that means when you have a little conversion, it will be slightly different. So how different exactly is this slightly different? So how about we'll substitute x and y in first. So in this kind of integration, yes, you will still have r is from 0 to 1. Yes, you will still have theta from 0 to 2 pi. And your x and y would not be changing from this form. So you have 1 minus, well, that means it is r squared cosine squared theta minus r squared sine squared theta, which is minus r squared. But now, you have to be aware, you will need to add on a Jacobian determinant, which you can represent that as partial x, y, partial r theta. So what exactly is this Jacobian determinant? So this, whoops, you need this over here, alright? So what exactly is this Jacobian determinant? How about we start from your simplest case, where you have your normal polar coordinates, conversion from x to r cosine theta, and y to r sine theta. Right, so how about we think about how do we convert this into polar coordinates? But since you might already know dx dy is just r dr d theta, but how exactly do you get the r in front? So that is where you have this Jacobian determinant. So you have partial x y, partial r theta, and this will be your determinant partial x, partial r, partial x, partial theta, or partial y, partial r, partial y, partial r, or partial x, partial theta. It will just be flipping it around. then partial y partial theta. So how about we take a look at what we get for your simpler case here. So when you differentiate x with respect to r, you have cosine theta. Differentiate x with respect to theta, you have negative r sine theta. Differentiate y with respect to r, you get sine theta. While differentiating y with respect to theta will give you r cosine theta. So how do we solve a determinant? Now, to solve a determinant, this 2 by 2 determinant, you will have multiply these two deducted by multiply these two. Alright? So r cosine square theta will be your first, and then you have to minus this to multiply together. So since you have a negative and another negative, that means you have to add. So this is your r. Now this is exactly how you get your r dr d theta, which is why when you have this kind of conversion, what you get in front of your dr d theta is an r. So how about let's take a look at this question that we have, the original one. So what will be your Jacobian determinant in this example here? Alright, so I hope that for this normal polar coordinates part you're clear of it. So once you're clear of that, it is pretty much easier to understand how to get this Jacobian determinant. So still, it is partial x, partial r, then partial x, partial theta, partial y, partial r, partial y, partial theta. So here you have your determinant, partial x, partial r. You just differentiate whatever you have up here, which will give you a cosine theta. Partial x, partial theta will give you negative a r sine theta. So partial y, partial r, you have b sine theta, while partial y, partial theta will have b r cosine theta. Right, so this is what you will be seeing. Now again, we use however you solve your determinant, which the first term is abr cosine square theta, so minus negative, which is plus abr sine square theta, and of course again your identity, and it will give you abr, which means abr is what we have over here. So we would just put it in. And since a, b here, we would take them as constants. That means we could just put them out of your integration. While at the same time, you can realize that everything within here is related to r. So you can directly integrate your parts for theta. Right, so you'll be seeing 2ab pi outside, since 2 pi from your theta, ab from within your integrand. And whatever's left inside is integrated from 0 to 1 square root 1 minus r square r dr. So in this part, you will just put your r inside while using up one of your tools from the outside. So ab pi integrate from 0 to 1 square root 1 minus r square dr square. So negative, and this will give you, so you can also directly integrate that at the same time, which square root 1 minus r square would give you square root 1 minus r square to the power of 3, but you have to multiply 2 over 3 in front, and then substitute in r is equal to 1 and 0. So the first part, when you substitute r is equal to 1, it's just 0. Then you substitute r is equal to 0, so this part is 1, but you have another negative. So your final answer will be 2ab pi over 3. Alright, so this will be the answer you have for this example. Right, let's take a look at what we just had. So, from your beginning, you take a look at this integration. It looks a bit weird. You try to figure out what exactly this graph is. And we find that it is an ellipse. Of course, an ellipse can be a circle, or can be, but not necessarily. So this ellipse here, we have to try to figure out some kind of method to change it into something that looks like polar coordinates. But in order to change that, we have to make use of your Jacobian determinant. So making use of Jacobian determinant, we find that it is that you have to multiply ABR. And then of course, the rest, you just proceed with your normal integration procedures. Alright? So I hope for this lesson, you're clear of everything so far. The main thing here is of course your Jacobian determinant. Well, when you want to change from Cartesian into polar and your functions aren't exactly the same, you will have to use Jacobian determinant in order to find out what will be the little changes. Alright? So I hope you pretty much understand it so far. I'll be ending this lesson here, and thank you for your watching.